Good morning, every expert. First of all, I'd like to say many, many thanks to Mr. President of Radix Philips and to Mr. President of Alter Technology, Mr. Yan, and to every expert here for giving the actual opportunity. And I do hope the actual times will bring you actual value, because I believe the actual value comes from the new concept. The new concept is proposed by Mr. Wang, president and founder of STEA A, the Beijing Talking Testing Engineering Academy Company Limited, located in Beijing, China. And this new concept represents more than 20 years of testing experience of Mr. Wang and his team. I'm happy to be the team member. So, what is the new concept? The new concept is the space radiation environment reliability. But why? It is new, since STEA did not find it anywhere. So STEA defined it. We defined it as the space radiation environment reliability is the capability or probability for any item to perform the specified function operationally under the space radiation environment, under the mission duration, and under, this is the most important, the specified top-level mission requirements. This new concept is creative. Why? It established a relationship between the top-level mission requirements and the bottom-level testing data. Why we say it is creative? Because we are individuals. Individuals like to perform things individually or separately, or to some extent, blindly. So, only when the whole community have one same language, have one same definition or concept, can the whole community have a whole picture. And then, only at this time, can so many testing data from different separate sources be meaningful for the different top-level mission requirements. So, I'd like to present 6, excuse me, how can I? Okay, the second. Oh. Okay, thank you. I'm sorry. Okay, to present 6 points. First, the background introduction. Second, space radiation effects. And the third is basic model. And fourth, the prediction method. And fifth, a case study. And then finally, summary and conclusion. So, as everyone here knows quite well, that satellite, airplanes, or computers at ground level, they work daily in the harsh space radiation environment. And therefore, the harsh space radiation environment is an important failure-causing factor. However, the traditional reliability prediction method did not include the harsh space radiation stresses. Can anybody find it in MIL Handbook 217? No. Can anybody find it in FINDES? No. So therefore, we think it is the right time to establish a method of space radiation environment reliability prediction. As everybody here knows quite well, the 3 stresses, SEE, TI, DDD, and the most sensitive devices, microelectronics, CPU, FPGA, etc. So, different sensitive devices at different orbits will encounter different stresses and therefore have different effects. Some are essential, some are accumulate, some are hard, some are soft. So here comes the big question. How can so many complex failure results get together to answer one question? The top-level mission requirement can meet or not. Traditionally, TIDD, SEE are considered separately. So there's no direct relationship between the failure results with the top-level requirements. And furthermore, in one satellite, such as GPS, the top-level mission requirements by itself differ in orders of magnitude. For example, for scheduled, unscheduled, long-term, short-term, hard failure software, the top-level mission requirements by itself originally differ in orders of magnitude. So the traditionally average designed TIDD, SEE failure levels may be over-designed or less designed for some different top-level mission requirements. So we established a basic model. This is the space radiation environment reliability basic model, which is the failure rate lambda space. It looks simple, but it can calculate for any item, for satellite, for airplane, for ground computer networks, from devices to equipment to subsystem, system to payload, or even to the whole satellite. It is simple, but it is created for 3 points. First, it sums up the failure rates of 3 independent TIDD, SEE failure rates, which was not possible before. Second, lambda space can be related directly to top-level mean requirements, which is also not possible before. The third, lambda space can be related with the bottom-level testing data, which was also not possible before. Therefore, by lambda space, the basic model, by the 3 possibilities, designers at every level can design precisely upon the different mission requirements without over-design or less design. So, this basic model can be used independently, but also it can be embedded into the traditional reliability models such as FINDES. We embed it through lambda physics by definition. So the failure rates for the space radiation can be added up to the failure rates of the traditional stresses, like temperature, etc. And then, with the basic model, we can calculate step by step. First, lambda SEE. As SEE is an instantiation effect only happens during power on time, therefore we need to know the fluctuations of the working time. And most importantly that we need to know every SEE type failure rate for every device. And for every SEE type, for every device, there are many methods, and this is a generally common European method, and we can input test data inside. And for TID, it is for engineering practice, it is normally regarded as non-normal if we have test data and we can calculate the distribution parameters, mu and the sigma, and then we can have the survivability. And with the same survivability at end life, we can transform from K-RAD to failure rate. That's the creation. So for simple understanding, we have a case study. Assume a satellite to be launched in 2015 on orbit GEO with design life of 12 years, and we calculate that mission space radius addresses for TID is about 70 K-RAD, and for single event effect, the LT structure is figure 1. And upon analysis, we know that SRAM at PGA is sensitive to TID and SEU, and we have done ground test with QBUG 60 for TID and heavy iron for SEU. And then here is the lambda TID calculation process. And then here is lambda SE calculation process. So with this basic test data and calculation, we can calculate lambda space. So summary. Mr. Wang from STEA proposed a new concept of space radiation environment reliability and proposed a new basic model. It is creative to establish the relationship between the top level mission requirements and the bottom level test data. Thank you very much for your time. Thank you.